Hello everyone, my name is Jinghua from Tianxin, China. My topic today is to break down the NXDOMAIN data in China and see what the result is. I only have 10 minutes, so I'm gonna go over the decks fairly quickly. If you have any questions, please feel free to contact me directly. My talk covers 3 sections: a little bit background information, then some comparison between our data versus root server data, and last some case studies. We are one of the biggest DNS infrastructure service providers in China, serving trillions of DNS queries on a daily basis. We also operate the biggest public passive DNS system in China, and that gives us a unique view into China's DNS data. For example, we have system in place to look for NXDOMAIN proportion, TLD distribution, domain patterns, and some other aspects. I'm going to show the results and some findings. Now let's see some comparison data. The diagram here showcases NXDOMAIN response trend over the last 2.5 years. The gray bar represents the L-root server. The blue line is our recursive resolver. We can see that our recursive resolver's NXDOMAIN rate is a quarter of the L-root servers. That's pretty much what we expected. Recursive resolvers face to user directly and often encounter repeated queries. On the other hand, root servers mainly handle top-level domains and are more likely to encounter non-exist domain names. Digging into our NXDOMAIN data, we categorize queries into 2. The majority, 81%, follow the ICANN's recognized the TLDs. The big ones are ARPA. Over half of the queries are PTR for private IPs, and CN, China CCTLD. And the invalid ones about 19%, and the biggest one is CTC, a special suffix used by a Chinese telecom operator. This table lays out the top 20 invalid TLDs we see with the most NXDOMAIN response. Take a look at the last column. It shows where these guys rank on the L-root server. We can see that half of these TLDs, like CTC, LAN, and Wi-Fi, are also big players at the root server level. But then you've got others, like CMP, not making the cut. Note the number 6 local sitting at 6 here, but topping at the L-root. We'll dive into local a bit more later on. For now, let's zoom in on the first CTC and the fourth CMP and see what's up with them. CTC is a special suffix used by a Chinese telecom operator. This telecom company has a massive user base, and the routers it provides to its user has a standard log address root.ctc, and this explains the huge volume of CTC NXDOMAIN that we saw. Most of CMP queries trace back to a few domains of a particular cloud service provider. Turns out a sneaky peek got added to their legitimate domain names because of a config mix-up, leading to the flood of NXDOMAIN response. For this take, we can see that 3 domains are behind 98% of all the CMP queries. The TLDs here typically associated with OpenNIC, Tor, and NameCom. Generally, these top-level domains don't leak into the public DNS. Their appearance here most likely have things to do with misconfigurations, such as someone testing things out in a sandbox environment, or simply incorrect usage, such as trying to access Tor domains through regular browsers. And it's an interesting side note that point to how diverse DNS queries can be. Now let's move on to some more common patterns. We dive into domain pattern analysis for a few key reasons. First off, it gives us the inside scoop on domain structures, helping us uncover the mysteries behind the NXDOMAIN response. Then, it's like our radar for spotting strange network behavior. These anomalies usually have a certain pattern to their domain structure, making them easier to catch. Lastly, when we find out the problem, we can contact a related party to help fix the issue, thus reduce the load of the DNS servers. Over nearly 5 months, we kept a close eye on NXDOMAIN response from our recursive resolver through hundreds of millions of unique domain names daily. We generalized the query names into regex-like domain patterns as shown in the third column, and we end up with two main buckets, those triggered by software issue and those by system config problems. On the software side, we are talking about things like prompt, advertisements, user tracking, black or gray application, blacklist service, and others. Configuration-wise, we have things such as device ID, reverse DNS, and FQDN end with search suffix. We can see that there are also 42% of domains that are not tagged a tab with a tab. They don't have much common patterns. Let's see some cases. In September 2022, we received a tip from a root server operation team who discovered a large number of DNS queries in the form of MAC addresses coming from China on their root servers. We quickly retrieved the data for verification and found indeed a substantial number of similar queries in the DNS logs, nearly 2 billion queries per day. Further analysis confirmed that this phenomenon was related to a very popular mobile application in China. We contacted a related party and soon the bug was fixed on September 18th, and such requests no longer appeared. When this application is in use, not only do we see DNS queries that look like MAC addresses, but there are also a mix of their query strings tagging along, like dev, WLAN 0, and a few others you see on the left there. These strings usually show up when this application checks the Wi-Fi hotspot status. On Android device, you can get a snapshot of a Wi-Fi hotspot real-time status with IP initial. The glitch in this application is it ends up broadcasting all these details in DNS lookups, which isn't supported to happen. Local is the special reserved name used in multicast DNS environment, which is different from the usage of public DNS. Let's look at its links to the public DNS. This diagram shows the distribution of all domains with top-level domain local in our recursive resolver. The first layer of the graph shows all domain names with the suffix local. The second layer shows the percentage of these domain names in different patterns, and the third layer shows the percentage of sub-patterns and their example domain names. We can see that uid.local accounts for 94% of all local domain. This means that mostly local domain follow the uid.local format. Further analysis reveals that uid.local is generated in a solution to the WebRTC privacy concerns, suggesting its widespread presence in public DNS might stem from mishandling an open source component. WebRTC is a free open source project. It allows web browsers and mobile applications to add real-time audio and video P2P connection and communication functionality. It allows users to quickly communicate with others on the web with audio and video. However, WebRTC has the risk of leaking the user's real IP address, both public and private. There is an IETF draft to address the problem of private IP being leaked. Specifically, it uses dynamically generated multicast DNS names, replacing the private IP with uid.local. MDNS is safe and doesn't affect public DNS. However, a high volume of uid.local queries could signal configuration errors or application-related glitches. On Android, we found out that when you use a certain video application and click on live broadcast, the application starts making uid.local queries. As mentioned before, top local queries on the root server maybe indicate similar issue with WebRTC usage around the world. This graph lays out the trend we are seeing with UID.local queries. Well, we couldn't pinpoint when they started. Our recursive resolver gives us a good look at how things have been changing. The blue line you see, that's tracking the sheer number of clients that have been hitting us with the UID.local requests, and we are talking millions here. And that's it. Thank you. And any questions?
Petr Špaček, I see. Can you go to the previous slide with the blue line? I have a question. If you identified, for example, some application which became popular or was released or updated or something around the July 2022, because it seems like very suspicious that I would expect like there is some like one reason.
I think it may be due to some live application.
Yeah, okay, thanks.
Ben Schwartz, Meta. So thank you for the overview of all these different interesting query patterns. I wanted to ask if you think these patterns represent ultimately a significant cost for your operations, or whether essentially they're not causing a problem.
This is different, and some patterns maybe have causing a problem, and some patterns don't need to address.
Sure. Could you mention, in that case, could you perhaps tell us of the patterns that you observed here, which of them is the biggest problem for your operations?
I think maybe local, because local in root is the biggest the DNS-OARC queries, but we have not more data to analyze and just an overview for UID.local.
Thank you.
Hi, my name is Shane Kerr from IBM. I think this is a super interesting presentation. I love when anyone digs into data and extracts patterns out. It's very nice. You mentioned at one point that you were contacted by a root server operator because of queries for the MAC addresses. Are you not, I guess this means that you're not running a local root, so you're actually sending all your queries to the root servers. Is there a reason you don't use local root?
Pardon?
Okay, sorry, maybe I'm not clear. So it's possible to configure a resolver so that you download the contents of the root zone, and then you don't have to send any queries to the root servers, which is quite common for large recursive operators like your organization. So is there a reason you haven't configured your resolvers that way, or that's my question, yes.
I think this problem may be contact our other friend to
okay.
answer your question, sorry.
Okay, no problem, thank you.